So actually, I would prefer micro plug and play, but PnP also works. So, yes, thanks for the introduction. Name is Fan Yang, as introduced, and I'm from KU Leuven, Belgium. Before I start here, I need to mention that this is a joint effort, and people in my team paid a lot of effort into the work. And special thanks to my supervisor, though, Danny, for his generous helping, first. And second reason is he's literally sitting in the audience, so let's get started now. So, Internet of Things. Nowadays, what we do is Internet of Things. We do a lot, actually, tons of application. First, there was a project called TreeNet from Switzerland. And what they do is they put sensors on the trees to measure the radius changing on the trees and study the relationship between the radius of the tree and the environmental changing. So that's pretty cool. And secondly, we have that's a node called DropTech and improving the cold chain logistics, especially for medical drugs and also the seafood we just had for the lunch, I guess. And thirdly, I want to talk a little bit about our smart lab, which is in our office building back in Belgium. So what we have is we have an espresso machine. We can monitor whether the windows are closed or open, the lights are on or off, and also we can see if people are actually using the room or so. We especially need to mention the espresso machine because you need to have an RFID card now to really get access, so nobody can steal coffee from us. Yeah, so we talk a lot about applications, but the reality is we actually don't have that many resources on the platform. Maybe I'll just do a small background, because most of our platforms actually are running on the power of battery, so that limits a lot of resources. For example, that's our current embedded platform, which is Arduino-based board plus a ZigBee radio. And you can see there is an 8-bit microcontroller. It can run maximum 16 megahertz. It's not really a lot. And also it only has 128 kilobyte of flash and 16 kilobyte RAM. How small is that? Actually, no, I did a small calculation before I came onto stage. Let's take the RAM as example. We don't really have 200, but we are planning to build 200 nodes in our lab. And if we add all the RAMs together, it takes more than 2,000 labs like what we have to actually get the same size of RAM in this machine I'm using for the slides. It's just a good impression. And also, it's very common for developers in Internet of Things to actually integrate peripherals into the platform. Well, by peripherals, I mean can be anything actually. A sensor, an actuator, maybe a network card, even though it's kind of difficult. But yeah, I mean anything you can imagine in embedded world can be a peripheral. So integrating a peripheral is actually not as easy as it sounds like. As a developer, a few things you have to go through. First, you have to physically connect your peripheral, that's of course, and you need to figure out which pin you connect to and which platform you're using. They're all different. And secondly, there are a lot of things you need to set. For example, the channel and the maximum, the sending rate or so. It's a lot of things you need to do. And thirdly, you need to write nasty, low-level driver codes, which typically you don't want to. And finally, but also very importantly, you need to deploy all the drivers you wrote for different peripherals. Just imagine we have 200, it's already a lot. And in real applications might be even more. Imagine, it's not like you can just grab your node and refresh your node at a table. It's not feasible like that way. So, in the end, things tend to become a little bit messy. Of course, by messy, I'm not only talking about the appearance from outside, it's also inside the codes. See, that's just two embedded programming codes for using SPI bus. It's simple, people use it every day. But just be aware that I'm not saying that's the problem. So in the end, when we go to production, all these things will be neat, all the wires will be gone, and all the code will be wrapped into libraries or so. But every time we have a new peripheral, we have to do all this stuff again and again. So that's the problem. And that's why we want to introduce the plug-and-play system. So micro plug-and-play. It's a plug-and-play style peripheral integration system for the Internet of Things. That's what the title said. So to do that, first we need to have a hardware part which can recognize such a peripheral. And next, we need to have a platform-independent software driver that is so compact, it's actually over-the-air deployable. And thirdly, we also want to have a network layer that can remotely discover and use your peripherals. So let's go step by step. First, I need to know which peripheral I'm using now. So each peripheral should have an ID. And how do we do that? We actually use resistors as peripheral IDs. And why? Because first, they're super cheap as far as I know, and they are globally available. You can buy it almost everywhere. And again, there's no extra chip you need on the peripheral side, which saves a lot of cost. I know it sounds almost too easy, right? What to do with it? However, I have to say, it's not perfect. Nothing is perfect, because first of all, they are never perfectly accurate. Well, for 1 or 2, maybe it's okay, but when you go for a lot of resistors, it's never accurate. And secondly, measuring this resistance will use your valuable ADC converters, because your peripherals will be fighting for those ADC converters, trust me. So, how do you deal with that? Well, here's how we did. We used a so-called multivibrators to convert the resistance value into a time domain signal, typically a time pulse, like indicated in the graph. Another thing, a good thing about that is, in time domain signals can be easily daisy-chained into one signal. What does that mean? That means actually you don't need all those analog channels on your chip. You actually only need one digital I/O pin, which saves a lot of resources on your chip. And we use 4 resistors to generate a unique ID for each peripheral with a 32-bit range. And there's a photo with the hardware board we have right now. It's also based on Arduino pin outs, and people who attended the demo yesterday might already recognize it. So, yeah, before we finish the hardware part, we need to claim we don't want to create any extra particles, or we don't really want to replacing anything existing already. So any existing peripheral can be easily wrapped into a micro plug-and-play peripheral by literally adding 4 resistors, which last time I checked is less 1 cent cost. That's kind of cool. Okay, so we already have a hardware identification. So now the peripherals are recognized. Now what do we do in the software? Well, you need to know what do we need to learn from the peripheral before we can use them. A few things. For analog peripherals, you need to know the actual transformation equation from the voltage value to a value that makes some sense related to your phenomenon you are watching. And secondly, you also need to know a maximum updating rate or so. For digital ones, take I2C example. You need to know the data register addresses, how the data is structured, and also which command should I send to read those data or write to the to write to them. Okay, I guess then we have to find out from datasheet. But I don't know how many of you actually read about a whole datasheet. They're not really straightforward. Let me just take one example. Just like the most easy sensor we can use is a temperature sensor. It generates a value that's correlated to related to the temperature. As easy as that. So here is a few pages I got from the datasheet. All right, so we got a lot of nice graphs and a lot of data, but wait, where is the transformation equation? The formula we're looking for, where is it? I don't see it actually. Well, just don't get me wrong, with all the respect, I respect guys' work, they are great. Most likely, most cases they are all correct, but it's just not user-friendly, you know? When I look for the formula, I don't see it. And in the end, we have to really calculate the formula by ourselves using some of the constants in the data sheet. But wait, that's only half a problem, because then each of platform you're using is different. Which channel I'm using right now? So I want to use I2C. Which pin should I connect? Every platform they're different, and how do I find out? I guess again the datasheet is the only choice. And yet, there it is. Same problem here. It's not straightforward. And that's when we say, okay, so developers should not worry about lower-level platform-related concerns. That's why we say we want a strong separation. First, we need a guy who is responsible for all the platform-related low-level concerns. And secondly, we have a guy with knowledge about drivers, peripherals. And the first guy doesn't necessarily need to know what the second guy is doing, and vice versa. And that's how we build our software stack. Just by looking how it actually works. So first of all, the peripheral ID will be generated from the hardware, so no problem with that. And after we got the peripheral ID, and we will see, okay, we got the ID of 12B23OF, whatever. Okay, channel is number one. Which driver should I use? I don't know. Just ask. Then driver request is sent to the server, and server will reply. Okay, that's driver C in this case, and driver C will be downloaded and installed automatically. So no more worry there. But do note, we have two different areas with different level of code. First of all, we have a platform-related native interconnect libraries, which is literally just ADC libraries, and UART, I2C, and SPI, whatever you can imagine. And that's the job of the platform developers. And secondly, we have a driver, the compact drivers that is for using the peripherals, that's the driver developers work. So in this case, both of them works are strongly separated. Since we're talking about the drivers, let's take a closer look. We defined a domain-specific language for the driver, and here is a small example of using a UART-based peripheral. So first thing is event-based, because we find out event-based is like a natural fit for the interrupt-driven nature of Internet of Things. And secondly, these drivers will be compiled into bytecode that is very compact, that can be over-the-air deployed in runtime. And also notice there are two different kinds of operations. The things marked in black are typical local operations, and the things marked in red are network operations, which will come in a minute. Okay, so far we have a driver prepared for the peripheral we recognized. Okay, so how do we remotely use these drivers, use these peripherals? That's how the network typically look like. So in network area, we define 3 different entities for the 3 different things. So first of all, we have the micro plug-and-play thing, which runs on top of the embedded platforms. And secondly, we have a micro plug-and-play manager, which runs in a server-like machine, and he keeps all the reference and all the corresponding drivers. And thirdly, we have the client. The client can be either a standard PC or it can be another embedded platform, depends on what kind of application you're looking for. So all these entities are connected using IPv6. And initially, the micro plug-and-play thing will have a unicast address, and the manager will have anycast address in terms of redundancy issues. So let's take a look how things happens in the network place. First, we plug in a few peripherals. The peripherals will be recognized. And as we mentioned before, the driver request will be sent to the manager. And the manager says, OK, I have the driver for you, and sends back the driver. And the driver will be installed. And after the driver being installed, the node itself will automatically generate a set of multicast addresses that's using the same peripheral ID for each peripheral. For example, we have an example here. The multicast address will include a multicast prefix, a network prefix, of course, and in the very end, we have the peripheral, the 32-bit peripheral ID that we used for recognition or for identification. So, since then, the node will say, OK, so who is the client? I have some new peripherals here. You'd like to see the data? And then, as a client, the client can read, write, or stream the data from the platforms using those multicast address. And that's why it's so efficient in the network side. So that's more or less what we already done here. And in terms of evaluation, first of all, we have energy consumption evaluation comparing between the micro plug-and-play and the USB. And the reason we pick USB in this case is because USB is like the mark of plug-and-play, and also we don't find any other equivalent things in the embedded world. And actually, that's not really a full version of USB. It's like a USB shield for Arduino. So people use it in embedded devices to create a kind of USB connection. First thing, this comparison is based on a 1-year usage. And we notice less frequent you're changing a peripheral, less energy it actually consumes. And that's why the horizontal axis is actually the frequency of changing peripherals, and the vertical axis is the energy consumption. And both of them are in logarithm scale. The USB will be assumed to stay in idle mode to create a sort of worst case for micro plug-and-play, because in that case, USB will be basically using the very minimum energy. So for a typical situation, like we say we change the peripheral every 1 day or so, we can clearly see the micro plug-and-play use much less energy, actually 6 orders of magnitude less energy than USB, which is a lot. And secondly, we also have the stack overhead analysis. So in this case, we count all the software stack, including a peripheral controller, the virtual machine, a few libraries, and also a network stack. So in total, they took 15 kilobytes of flash and only 2 kilobytes of RAM. I think it's really thin layer of software stack. And in terms of development effort, we compared the same drivers written both in micro-PnP language, the domain-specific language, and also the native variant language, which in this case is C. And we can see that for typical situation like analog ADC sensor, the driver written in micro-PnP language is much, much smaller. In this case, less than 30% from the native language. So we can safely say that by using this kind of driver language, it saves a lot of effort from developers. And finally, we also did a small network performance analysis. So in this case, we did generate multicast address and join the multicast group, request the driver, and install an 80-byte driver, and also advertise this peripheral. In total, it took less than 200 milliseconds. I think that's reasonably pretty fast. So what's going on next? First of all, while we are speaking right now, our boards are being manufactured somewhere in China, I think, and we are going to build a much larger scale test bed. Secondly, as some of you might already see it yesterday, we have a next generation node which is much smaller. And sorry, I don't have a banana in this picture, but it's more or less the socket size, power socket size, sorry. So that's more or less the very end of my presentation. What I've been talking about, micro-PnP enables plug-and-play fashion in Internet of Things. It's a very very limited energy consumption and very limited cost. Also, it saves a lot of developing effort, and it has a very efficient networking. We're looking forward for people who are interested to join us in the beta version test. But right now, that's the end of my presentation. Thank you.
Questions? No question? I have a question. You quantified the software costs of the approach. I imagine if I understood correctly, then you have to put a hardware controller into these devices as well to support the micro PnP. What would be the hardware cost for this controller?
Good question.
Here you go.
Sorry. So right now we're using a first version of our hardware, which is a picture in a few slides ago. Right now it's under development. We trying to minimize the cost, but I think the final cost is going to be around $5 or so for each board. But on the other hand, the peripheral side will be really minimal. So I think in real applications we will face much more peripherals than control boards. So.
Thank you. Any further questions? Everybody's waiting to go to the banquet. Okay, let's thank the speaker again.